A partial function is a function which may not be defined on its entire domain. For instance, we could define a partial function from 0, 1, 2 to 0, 1, 2, 3. And because it's partial, we don't have to define all of the inputs having output. For instance, we could just say f of 0 is equal to 1 and f of 1 is equal to 2. Because it's a partial function, we don't have to define f of 2. All functions are partial functions. Another example of a partial function would be just any function that we define. So we could look at g, and if we define g from 0, 1, 2 going to 0, 1, 2, 3, then we could have g of 0 equals 3, g of 1 equals 0, and g of 2 equals 1. And this would be a nice example of a function, but a function is also a partial function. So notice it just says may not be defined on the entire domain. And this is an instance where the definition is very terse, but it's intended to do something very specific. The functions you know are partial functions. It's just that these other things where you don't have everything defined as a partial function. Also, you could have something where there's nothing defined. It's perfectly valid to say f of 0 is undefined, f of 1 is undefined, f of 2 is undefined, and that's a partial function. It's sometimes called the empty partial function. Partial functions are definitely weird. There's no denying that. As I think about how I might try to think about them, one possibility is I could just try to start listing them all. I'm letting a equal 0, 1, 2, and I'm letting b be just a set containing 0. So it's a one element set. And then I can ask myself, okay, what are all the partial functions from A to B? And now I have to think, okay, what did I do? Well, I have 0, 1, or 2. And I could say f of 0 is 0, or I could say f of 0 is undefined. So for each slot, I have two choices. I can either set the value to be 0, which is the only element in the codomain, or I can choose to set it and leave it undefined. So the number here is 2 times 2 times 2, which is 8. Now, as soon as I see that I'm close to 10, and if I actually stopped to try to list them all out, I could probably do it. I could probably list out all the possible partial functions in a systematic way. But as soon as I see that 0 gets me close, I can probably take the next step and see that 0, 1 gets me there. And the reason for this is I get all of the functions that I had before when all I had was 0. But now, so everything that only used 0 is still legal. And that got me 8 total, I saw just a second ago. So as long as I can make up 2 more, I can make up f of 0 equals 1, f of 1 equals 0, f of 2 equals 0, and I can make up f of 0 equals 0, f of 1 equals 1, and f of 2 equals 0. And that gets me 2 more, and now I'm past 10, and I can make up several more actually. So that's one approach, is just to use a kind of Polya principle where you start with small values and you see what you can get. That's perfectly legitimate because your goal is just to find the first number that eclipses 10. I think the challenge here is grasping the definition of partial function and realizing that even in that short definition, it gives you all the information you need. The second approach might be that if you go searching for more information about partial functions to get a clearer picture, so if I just search for partial function and just look at the Wikipedia page, it discusses the definition I've described here, but says it in a different way. So in mathematics, a partial function from a set x to a set y, I don't find that helpful at all, unfortunately. So I'm going to try a different source and see if that's clearer. Actually, this is probably better. It at least gives me the example that division is a partial. That's not true at all. So it's actually a terrible definition. I like this idea the best. It has some nice pictures. There are many examples here that might be helpful. But what I really care about, I mean, that's incredibly abstract. And maybe I just want to know how many there are. So is there a formula to count partial functions? So someone has already asked this question. If A and B are two sets where the size of A is k and the size of B is n, prove that the number of partial functions from A to B is n plus 1 raised to the k. And you might remember that this matches the formula more or less for the total number of functions, the number of actual functions, what are called total functions from x to y, is the size of y raised to the size of x. Question that we found online is saying is that the number of partial functions from x to y is given by the size of y plus 1 raised to the size of x. And I mean, there's an obvious relationship here, and this is something that we can work through with product principle. When we construct a partial function from x to y, we can really think of that as a function if we add an additional element to y called undefined, because we are allowed to have things that aren't defined here. So that it makes it very clear that if we're trying to make our partial functions here, we have something for our first element in x, a second element in x, something all the way to whatever the last element in x is. And our job here is to give each of these a value. So we have y plus 1 options for each slot. And this is a really nice application of product principle. I'm going to be honest, when I wrote this question years ago, I did not know that there was such an elegant solution. I intended it to be an application of brute force, but I like it better now that I know. And so I've learned this proof from a student who found it somewhere online. And it's a nice example of someone teaching me. So the way to think about this is for each element in x, we have y plus 1 options to map to. Either an element in y, which there are size of y options, or an element called undefined, which has 1 option. So there's sort of a sneaky sum principle showing up in how we get to the y plus 1 options. If you think about it this way, there's y plus 1 options, size of x numbers of times. And that's why this is the result that it is.